Hello, today we're going to talk about structure 2.2.5 and 2.2.6, and this is all about bond polarity and molecular polarity. So let's talk about bond polarity first. You can have polar bonds or nonpolar covalent bonds. And this, of course, is just talking about covalent. But if you have something where you have two of the same atom bound with a covalent bond, like these two chlorines, they have the lone pairs. We know that chlorine is going to have the same electronegativity as chlorine because they're the same atom. Electronegativity is how much the atom is attracting electrons that are shared in the bond. So if they're both pulling on the electrons evenly, they're evenly sharing, that is a nonpolar bond. But if I have something, let's say I have hydrogen attached to chlorine. The hydrogen atom and the chlorine atom have different electronegativities. Chlorine is more electronegative than hydrogen. So the two electrons that are being shared in this bond are more likely to spend time around the chlorine because it attracts the electrons more. So you wind up with a very slightly positive charge on the hydrogen and a very slightly negative charge on the chlorine. Greek letter there just means partial, so like a partial positive, partial negative. So because it's not sharing those evenly, we call that a polar bond. It is still a covalent bond. They're still sharing their electrons, but it's sharing unevenly. Now, you have in your data booklet the electronegativity values for the different atoms. It's one of the very first sections. Remember that your data booklet has a table of contents, so you can very easily find the different sections. So electronegativity is on one of the periodic tables near the front. And you can look at the difference in electronegativities. If the difference is very small, then it's more likely to be a nonpolar bond. If you have a much larger difference in electronegativity, it's going to be more likely to be a polar bond. That is until you get to metals with nonmetals, like sodium with chlorine. Well, the difference in electronegativity between those two is much, much greater. So much so that effectively the chlorine winds up stealing the two electrons, or really stealing one electron from sodium. And they wind up with full positive on the sodium and a full negative on the chlorine, and that is an ionic bond. So you can see the difference between an even share, a partial share, right, like an uneven share, so that you get partial positive, partial negative, or a complete transfer where you get a full positive and a full negative. There's also the bonding triangle, and the bonding triangle is a little bit later in the data booklet, but there's actually like a formula for determining whether you're looking at ionic, polar covalent, or nonpolar covalent, and it has to do with both the difference in electronegativity and the average electronegativity. So I encourage you to look at that, and if it's like one of those borderline, you're not sure whether it's going to be nonpolar or polar, or even polar versus ionic, I would suggest using the equations on the bonding triangle instead, so you can be absolutely sure which type of bond you're looking at. Okay, now let's talk about molecular polarity. And so this is a little bit different, and it depends on the Vesper shape. So you really need to make sure that you know your shapes, your geometries really well. So let's go through our different shapes. If I have something that is linear either has two atoms like that or just one atom. That would be linear. If you have two of the same atom on either side and no lone pairs on the central atom, then it's going to be nonpolar overall. So I want you to think of molecular polarity as a type of symmetry. So you're looking not just at whether they're sharing evenly among the bonds, but whether they're sharing evenly kind of around the entire molecule, the electron density around the whole thing. So let's say I have carbon dioxide. Carbon dioxide is a linear molecule like this, and you have the same atom on either side. There's no lone pairs in the carbon, which keeps it linear. And so because of this, oxygen is more electronegative than carbon. You wind up with these somewhat polar bonds. But because they're arranged on opposite sides of the carbon, those polar bonds effectively cancel each other out. So you have slightly negative, slightly positive with the carbon, but their location around the central atom cancels each other out, making it nonpolar overall. So the location of the polar bonds matters. Well, let's look at another example. Let's say I have something like HCN, also linear. This one's going to be more of a non-polar bond, and this one is definitely going to be polar because the nitrogen is a good bit more electronegative than the carbon. So effectively, you're winding up with more of a negative charge on this side, more of a slightly positive charge on this side, and so they do not cancel each other out, giving this a polar molecule overall. But another good way and relatively easy way to tell is if you were to cut the molecule in half. Is it the same on both sides? Then it's likely to be nonpolar. If it's different on both sides, then it's likely to be polar. All right. So same on both sides is nonpolar, different would be polar. And that's for linear. Now linear is one of the easier ones to see. So let's go ahead and look at like trigonal planar. There's trigonal planar. Now if all three of those atoms are the same, then it's likely to be nonpolar. So like if I have BF3, all three of those fluorine atoms have the same electronegativity. Those polar bonds cancel each other out, making this nonpolar overall. But if I have something that is a different atom, like this one, this side becomes slightly negative and this side is slightly positive because oxygen is more electronegative. So the bonds do not cancel each other out, and making the molecule polar overall. And you can tell that there's pretty clear, like if you cut it in half, there's different on both sides, making it polar. So that's for trigonal planar. Now, if you were to change one of those into a lone pair, that would be bent. And then it would be definitely polar because that one lone pair causes it to always be uneven. So if you see bent, it is always polar. And now our other geometry that I want to talk about really quick is trigonal planar. I'm sorry, it's tetrahedral. We already talked about trigonal planar. Tetrahedral has 4 atoms around the central, like this. But remember that it's actually in 3D. So in reality, you're going to see that 109.5 bond angle. And so it looks kind of like a tripod with something sticking out the top. So if you have something like CH4, methane, where all of those bonds are the same, it's completely symmetrical around the central atom, it's going to be nonpolar. If I were to change any of them into a lone pair, like ammonia, I'm running out of space, ammonia would be trigonal pyramidal, that's polar because of the lone pair. I don't know why I would draw oxygen, it should be hydrogen. That one's polar. If I change 2 of them into lone pairs, like water, definitely polar. So if you see lone pairs from that tetrahedral starting point, definitely polar. But I do want to caution you about one scenario with tetrahedral. I'm just going to take up some space here from linear. Sometimes you'll see them draw because tetrahedral is 3D, but they draw it on flat paper. So if I see something like this, okay, so CH2F2. That looks like it might be symmetrical, right? Like if you draw a line down the center, it looks the same on both sides, or if I draw a line horizontally, it looks the same on both sides. However, you have to remember that it's 3-dimensional like this. So in reality, it's going to have 109.5 bond angles, like this. And so if you were to like rotate that around and view it a little bit differently, you might draw it more like this. And that is the same exact molecule as the one I drew before. So again, if I have the fluorines on opposite sides or the fluorines on the same side, these two molecules are exactly the same. They're just drawn differently. And so you need to be really careful with those representations, because either way, this is a polar molecule. The carbon fluorine bonds are polar bonds, and they do not cancel each other out because of that three-dimensional space. I really recommend trying to build models of these and take a look at them in 3D, because sometimes it's really hard to picture from just a flat image. And they could try to trick you by giving you a drawing like this one here, which looks like it's non-polar, but is definitely polar. Okay, so this one wants us to place the following bonds in order of increasing polarity, and I gave you a little cutout here from your data booklet showing the electronegativities. Electronegativities are on the bottom of the box. So you just find the difference in electronegativity. So the difference for the nitrogen and oxygen is 0.4. The difference for the nitrogen and the fluorine is 1. The difference for hydrogen and oxygen is 1.2. And the difference between hydrogen and nitrogen is 0.8. So if I'm doing increasing polarity, you go from the smallest and then go next largest, and then our largest one yet is the HO. So this is the least polar to the most polar. All right, and then for this example, it wants us to predict whether the following molecules will be polar or nonpolar. If I have HCN, again, the best way to go about this is to draw those Lewis structures. There's a triple bond. And so this one is very clearly asymmetrical. This one's polar. C2H4, if I were to draw that, would have a double bond in between. This one is very symmetrical around those central carbons, and it is nonpolar. CLF is just the two atoms like this. And so this one would be polar. If you wanted to like compare it to other polar bonds, you would need to use the electronegativity values, but you can tell that it is at least slightly polar because they are different atoms. Compared with F2, which has two of the same atom, which is very polar. So polar, nonpolar. Oh, I mixed those up. Just be careful with that. This one is the polar one because it's asymmetrical, and this one is the nonpolar one because it is symmetrical. Right, so this links to some of our bonding sections. So what properties of ionic compounds might be expected in compounds with polar covalent bonding? If you have polar covalent bonding, like my HO bond, and typically it's going to form at least one other bond, but you have a slightly positive charge on the hydrogen and a slightly negative charge on the oxygen. That is an uneven sharing of electrons. Well, this is going to be able to interact with, say, negatively charged ions. So polar compounds can dissolve ionic compounds. They also can dissolve in other polar things. So if you see like ammonia. Ammonia is also a polar molecule, so you have a slightly negative charge and slightly positive charges. The slight positive from, let's say this is a water molecule, can interact with the slight negative here, and that causes the ammonia to dissolve well in water. So ionic compounds tend to be fairly soluble in water because of the charges, but also polar covalent compounds can also typically dissolve in water because it is polar as well. So it says, what features of a molecule make it infrared active, IR active? Well, you'll get into this more in a later section, but effectively, the more polar a bond, the more IR active it's going to be, effectively. When you get to, let's say you have your molecule here, and let's say that these are different atoms. So you have this polar molecule. Infrared radiation causes these bonds to bend and stretch. So you'll see slight bending toward each other like this, or even this way. So slight bending, and then you'll also see some stretching involved. So you'll see stretching across this way. And if those bonds, when they stretch, change the polarity of the molecule, so let's say, for example, that this side is my negative side and this side is my positive side. And if it's stretching this way, you're going to wind up with a slightly less polar molecule because your positives and negatives are closer together. But when it stretches this way, that's going to wind up being slightly more polar because the positive and negatives are further apart. We can call that the dipole moment. Right? The more polar it is, the greater the dipole moment. It's just a fancy way of talking about it. But effectively, anything where those bends and stretches changes the polarity of the molecule makes it infrared active.